Tonight, we're going to explore one of the most demanding undertakings ever imagined by human beings. Not visiting Mars, not planting a flag and coming home, staying there, building a life on a world whose surface averages 60 degrees below zero, whose air sits at less than 1% of Earth's pressure, and whose thin sky lets through 250 millisieverts of radiation every year, roughly 100 times what your body absorbs at home. Every breath you take on Mars has to be manufactured. Every drop of water has to be mined. Every calorie has to be grown in soil that has never known life. And yet none of those may be the hardest problem. Hidden beneath the engineering challenges is a single obstacle that could determine whether a Martian civilization survives for centuries or never truly begins at all. Every system that keeps you alive depends on every other system holding. One failure cascades. One missed launch window costs 2 years. One torn seal can end a settlement. By the end of tonight, you're going to understand why surviving on Mars is not a single engineering project, but a stacked negotiation with physics, biology, and human identity itself, how the rocket equation, the Hohmann transfer, and supersonic retropropulsion shape every decision before launch, and what it would actually mean to turn a hostile second world into a permanent home. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Mars does not ease you in. It arrives all at once. Start with the cold. The average surface temperature on Mars sits at around 60 degrees Celsius, which is 80 degrees Fahrenheit. That is cold enough to make steel brittle. Cold enough that unprotected skin would begin to suffer frostbite, not in minutes, but in seconds. And that is the average. At the poles, temperatures can drop to 125 degrees Celsius, close to 195 degrees Fahrenheit. A temperature range that would shatter most unprotected mechanisms we rely on for survival. A pressure suit on Mars is not clothing. It is a thermal machine. It has to hold a narrow band of warmth around a human body while the outside world tries to pull every joule of heat away through the suit walls, through any exposed surface, through any crack or seam that is less than perfect. The suit generates internal heat from heaters, from electronics, from the body itself. That heat has to be managed, routed, expelled in controlled amounts. Not too much, not too little. A failed pump during an EVA, an extravehicular activity, a trip outside the habitat, can allow core body temperature to drop in minutes. What your brain codes as going for a walk becomes something closer to a dive below the surface of a frozen ocean. Every step is a controlled operation. Every step depends on a system holding. Temperature is, in a strange way, the part your brain understands. You know cold. You know you need insulation. You know the stakes are immediate and visible. The next layer is harder to see, and harder to fix. The Martian atmosphere weighs almost nothing against the surface beneath it. The pressure at the Martian surface sits between 6 and 7 millibars. Earth's atmospheric pressure at sea level is roughly 1,013 millibars. Mars runs at less than 1% of that. To find air this thin on Earth, you would have to climb to the upper stratosphere, roughly 35 kilometers up, where even a perfect oxygen supply would fail you. Because at that pressure, your lungs cannot pull enough oxygen from each breath to sustain consciousness. The partial pressure is simply too low, but thin air is only part of the problem. The Martian atmosphere is not depleted oxygen. It is almost entirely carbon dioxide, about 95%. There is trace oxygen, but trace means trace. Breathing the Martian atmosphere without a sealed suit is not suffocation in the slow sense. It is faster than that, and stranger than that. If a helmet seal fails, oxygen stops reaching the blood. At the same time, the drop in pressure means that the liquids in the human body begin to behave differently. Water boils at lower temperatures when pressure drops. At Martian surface pressure, water boils at a temperature the human body already maintains, which means bodily fluids, including saliva, can begin to bubble and vaporize. Unconsciousness comes in seconds. Death follows in minutes. This is not a dramatic extrapolation. It is straightforward physics, applied to a biological system. Every habitat on Mars, every rover, every suit has to maintain a permanent pressure differential between its interior and the outside world, the way an airliner cabin maintains pressure at altitude, the way a submarine holds pressure against the surrounding ocean. But an airliner flight lasts a few hours. A submarine mission lasts weeks. A Mars colony is not a mission. Every weld in every module, every window gasket, every airlock seal has to hold that differential for years, through temperature swings that cause materials to expand and contract, through dust storms that scour surfaces with fine abrasive particles, through micrometeorite impacts, through mechanical vibration, for as long as the colony exists. Here is where it gets strange. The gravity layer sounds, at first, like a benefit. Mars has a surface gravity of 0.38 g. A person who weighs 90 kilograms on Earth, about 200 pounds, would feel like they weigh about 34 kilograms on Mars, about 75 pounds, lighter, more mobile, less strain on the joints. The intuition is that lower gravity is kinder to the body. Wait, that intuition is exactly backward. Human bones and muscles are not just structural, they are dynamically maintained systems. Load-bearing gravity is part of the signal that tells the body to keep them dense and strong. Remove the signal, and the body begins to dismantle what it no longer thinks it needs. We know this from the International Space Station. Astronauts in microgravity, true zero gravity, lose bone density at a rate of 1 to 2% per month in load-bearing regions. Muscle mass can shrink by double-digit percentages within weeks, even with intense exercise regimens designed to fight the loss. Mars is not zero gravity, but here is the problem. Mars is not Earth gravity either, and no human being has ever lived at 0.38 g for an extended period. We do not know what 0.38 g does to the body over months, over years, over decades. Every person who settles on Mars becomes a long-term biological experiment with no control group and no established baseline. The outcomes could include slower bone loss than microgravity, but still significant loss. Spinal elongation, joint reshaping, a cardiovascular system that gradually remodels itself for a lighter gravitational load. And there is a question underneath all of that, one with no current answer. Children born on Mars, raised in 0.38 g from infancy through development, may grow bodies that are tuned to Martian gravity in ways that make Earth's gravity physically dangerous. Not uncomfortable, not difficult to readjust to. Physically dangerous. A body shaped by 0.38 g, with bones and muscles and a cardiovascular system calibrated for that load, placed into Earth's gravitational field for the first time, might not tolerate it without significant medical intervention. Martian-born humans may never be able to come home, not because of politics or economics or a lack of transport, because of physics. The fourth assault is invisible. Mars has a thin atmosphere and no global magnetic field. Earth has both, and both matter enormously. The atmosphere absorbs energy from incoming cosmic rays and solar particle events. The magnetic field deflects charged particles before they reach the atmosphere at all. Together they reduce the annual radiation dose at Earth's surface to about 2 to 3 millisieverts per year. For reference, a CT scan of the abdomen delivers about 10 millisieverts in a single session. On the Martian surface, with neither shield in place, the annual dose runs somewhere between 200 and 250 millisieverts. Living on Mars for a year delivers roughly the equivalent of more than 20 CT scans, every year, indefinitely. The damage is cumulative and slow. DNA strand breaks that accumulate faster than the body's repair systems can address them. Elevated cancer risk over a lifetime. Possible effects on brain function and cardiovascular health that researchers are still working to characterize. The radiation does not announce itself. You cannot feel it arriving. The solution requires burying. 2 to 3 meters of Martian regolith, the loose surface material piled above habitats, blocks the incoming dose down to manageable levels. Water tanks, food stores, fuel reserves, and waste containers arranged around living spaces provide additional mass-based shielding. The practical result is that early Mars bases will not look like the glass and steel structures that appear in visualizations. They will look like underground facilities, Buried modules, tunnel networks, lava tubes sealed and pressurized. Mars itself becomes the armor, because there is no other armor available in sufficient quantity. The fifth layer does not kill you quickly. It wears at you. The minimum signal delay between Earth and Mars is several minutes one way, when the two planets are at their closest. At worst alignment on opposite sides of the Sun, a one-way signal takes more than 20 minutes. A question asked of Earth takes 40 minutes to receive a reply. A medical emergency cannot be managed in real time by Earth-based specialists. A crisis in the habitat cannot be coordinated by a team of engineers sitting at consoles on another planet. The colony is functionally alone, and the physical reality of that aloneness is relentless. A few pressurized rooms, a few tunnels, the same faces, every meal, every day, for years. Outside the windows, a dead landscape, no forests, no oceans, no open sky that is breathable. Antarctic research stations and submarines have already shown what extended confinement with a small group does to human behavior. Elevated stress, depression, interpersonal conflict. Antarctica and submarines have rescue available within a reasonable window. Mars does not. Psychologists, clear community rules, private space, and formal conflict resolution structures are not amenities for a Mars colony. They are safety systems in the same category as the airlock. 5 fronts, operating simultaneously, permanently: temperature, pressure and atmosphere, gravity, radiation, isolation. None of them pauses while you address the others. The cold continues while you manage the CO2 scrubbers. The radiation accumulates while you treat the fractured bone that healed differently in 0.38 G. The psychological pressure builds while the technical systems demand attention. Living on Mars is not solving a single hard problem. It is maintaining an answer to 5 hard problems at once, every hour, for years, with no margin for a cascade and no quick way home. And that is before a single colonist has even left Earth. Before anyone is breathing that thin air, they have to cross the gap to it. And crossing the gap is not a matter of distance. Distance is almost the wrong word. It is a matter of energy. Specifically, it is a matter of delta V, the total speed change a vehicle can achieve by burning its propellant. Everything in spaceflight is governed by delta V. It is the currency of the business. To reach low Earth orbit, a rocket must accelerate to roughly 9.4 kilometers per second. That is about 21,000 miles per hour. From there, the crew is not at Mars. They are simply in a stable orbit around Earth, still well inside Earth's gravity well, still nowhere near the journey's beginning. To push from low Earth orbit onto a transfer trajectory toward Mars, the spacecraft must burn again, adding roughly another 3.6 kilometers per second, another 8,000 miles per hour of velocity. And when the spacecraft arrives at Mars months later, it is still moving at interplanetary speeds. It has to slow down or it will fly past Mars forever. That deceleration costs more delta V still, but the reality is different. Every kilogram added to the spacecraft makes this exponentially harder, not just a little harder. This is what the rocket equation describes, and it is a punishing relationship. Extra habitat modules, extra food, extra water, extra radiation shielding, extra tools, extra spare parts, extra medical supplies. Every one of them adds mass. That extra mass requires more propellant. The propellant itself has mass, which requires more propellant to carry. The requirement compounds on itself. A rocket built to deliver a human crew and a viable colony's worth of supplies to Mars is not a slightly larger vehicle than one delivering a small robotic probe. The scale is something closer to a skyscraper-sized structure in which most of the volume is propellant, and the actual delivered payload is a comparatively small fraction at the top. Any path to cheaper Mars missions runs through fundamentally better propulsion, large-scale in-space refueling, and reusability at levels well beyond what is routine today. And that is before the launch window problem. Earth and Mars do not stay in the same relative position. Both orbit the Sun, but at different speeds, tracing different paths. The geometry only lines up favorably for a fuel-efficient transfer roughly every 26 months. That alignment is called the Hohmann transfer window, named for the German engineer Walter Hohmann, who calculated the mathematics in 1925, miss it, and the crew does not get a second chance a few weeks later. They wait approximately 2 years for the planets to come back into alignment, or they burn far more propellant on a less efficient, longer, and riskier path. For a colony, this 26-month rhythm governs everything. Cargo shipments are not continuous. Crew rotations are not continuous. Every spare part, every replacement module, every resupply package must fit into launch windows that come around on a planetary clock. A critical component that fails shortly after a window closes may take nearly 2 years to replace. The Space Amazon concept, the idea of ordering something and receiving it on a useful timescale, does not exist. The colony plans years ahead, or goes without. The transit itself, the 6 to 9 months of travel between the two planets with current chemical rockets, is not a passive waiting period. It is its own chain of compounding threats. The human body in microgravity does not simply float comfortably. Muscles weaken without the constant resistance of gravity. Bones shed density because the body stops maintaining structure it no longer needs to load. Fluids shift toward the head. The heart, a pump optimized for a one-gravity world, begins to remodel its shape. The balance system, expecting a gravity signal that never arrives, starts to recalibrate in ways that create disorientation. These are the same effects observed on the International Space Station. For a Mars transit, the duration is comparable to or longer than most ISS deployments. Crews arrive at Mars already compromised. There is a further problem. The journey runs almost entirely outside Earth's magnetic field. Earth's magnetosphere shields the surface from the worst of the cosmic ray and solar particle environment. In transit, that shield is gone. The radiation exposure accumulates for every month of the crossing. Energetic particles stream through the spacecraft walls. They pass through tissue, they break chemical bonds. The accumulated dose over a 6 to 9 month transit is meaningful, and it arrives before a single day of living on Mars has begun. Countermeasures exist. A rotating section of the spacecraft can use centrifugal force as a substitute for gravity, partially limiting the physiological decline. The ship can carry a dedicated radiation storm shelter, a heavily shielded inner refuge built from the stored mass already aboard, water tanks, fuel, food supplies, stacked around the living core. Closed-loop life support systems can recycle water and scrub carbon dioxide from the air for months without resupply from Earth. None of these are trivial engineering challenges, and none of them are completely solved. And there is no rescue available mid-transit. Not a crew that falls behind, not a component that fails catastrophically, not a medical emergency. Whatever happens in the middle of the crossing, the crew manages it with the resources aboard the ship. There is nothing else. Wait. The most violent and dangerous part of the journey has not happened yet. At atmospheric entry at Mars is where spacecraft are won or lost. The Martian atmosphere is roughly 1% of Earth's sea level pressure. That sounds like almost nothing. But a spacecraft arriving from an interplanetary trajectory is moving at speeds that turn even that thin atmosphere into an enormous physical force. The friction is extreme, the heating is extreme, and the spacecraft must thread a precise corridor. Too steep an entry angle and the vehicle hits the atmosphere like a wall, generating forces and temperatures that break it apart or drive it directly into the ground. Too shallow and the atmosphere does not capture the vehicle at all. The spacecraft skips off the upper atmosphere the way a flat stone skips across the surface of water, deflected back into space on a useless trajectory with no path to a second attempt. For small robotic landers, parachutes combined with modest retro-rockets have worked. But a crewed lander, or a heavy cargo lander, the kind carrying tens of tons of habitat modules or supplies, is a different problem entirely. Parachutes alone cannot decelerate that much mass in an atmosphere that thin. The technique required is supersonic retropropulsion, firing rocket engines at full power while still moving at supersonic speeds through thin air. The engines must fight the incoming atmospheric flow and slow the vehicle enough to land safely. It has been demonstrated in early form. It has not been demonstrated at the mass scales a serious colony would require. And it must be repeated reliably for every habitat, every power system, every cargo run. A small error in guidance, a brief engine anomaly at the wrong moment, a slightly wrong entry angle, and the result is a crater. The supply chain wraps around all of it. Every kilogram safely on the Martian surface represents many times that mass launched from Earth. Hundreds to thousands of tons launched per tens of tons landed is not an exaggeration of the ratio. Every tool, every replacement seal, every medication, every electronic component must be identified and loaded years before it is needed, because the window to send it is years away, and the cost of each cycle runs into the billions of dollars. The colony, at least in its early decades, does not function like a city with a supply chain. It functions more like a remote Antarctic research base with multi-year resupply delays, extreme per item costs, and a permanent awareness that the delivery schedule is beyond its control. A funding pause on Earth, a geopolitical disruption, a run of failed launches, any of these can choke the line. The colony cannot simply order more. It makes do or it does not. Distance is not the problem. People say Mars is far away, and they mean it in terms of miles, in terms of time. But the real constraint is the energy budget to leave Earth, the 26-month clock governing when that energy can be spent efficiently, the biological cost of the crossing, and the narrow corridor at the end that must be hit perfectly. The journey is a fragile chain. Every link must hold, and that chain must be built, funded, and operated continuously before anyone has started the harder work that waits on the other side of it. That harder work begins with the air. Not the air outside. The air inside, the air being manufactured for them right now, in a chain of machines that must never stop. The colonists breathing in a buried module on Mars is not breathing Mars. They are breathing a product. Every molecule of oxygen in their lungs was pulled from a thin, mostly carbon dioxide atmosphere, scrubbed, separated, compressed, and delivered through a system with no backup planet. The Martian atmosphere is about 95% carbon dioxide. The remaining 5% is mostly nitrogen and argon, with trace amounts of oxygen and water vapor. Trace means almost nothing. The surface pressure is 6 to 7 millibars. Earth at sea level runs around 1,013. A human being stepping into that atmosphere without a suit would lose consciousness in seconds. The pressure differential is not a minor engineering inconvenience. It is the entire premise of survival. Inside the habitat, the air must be held at something close to normal breathing pressure, roughly 500 to 1,000 millibars depending on design, with the right oxygen fraction constantly. The life support chain that makes this possible runs in sequence. Compressors draw in the thin outside atmosphere. Scrubbers remove the carbon dioxide. Oxygen generators split water or carbon dioxide molecules to produce breathable oxygen. Each step depends on the last. Each machine depends on power, on filters, on seals that hold. Here is what happens when any link breaks. Carbon dioxide builds up or oxygen drops. The first symptom is a headache, then fatigue, then confusion, then unconsciousness. The full progression, under the wrong conditions, takes minutes, not hours, minutes. There is no slowly getting worse that gives you time to notice and fix it. The chain either holds or it does not. The habitat itself is not a building in any conventional sense. It is a pressure vessel. The interior pushes outward against the vacuum outside with every weld, every gasket, every window frame, every airlock seal under continuous load. Add thermal cycling, because Mars swings between temperatures that would make steel brittle and temperatures mild enough to feel temperate, all in the course of a single day. Add fine abrasive dust working into joints over months and years. Add micrometeorite impacts, small rocks moving at several kilometers per second, too small to see coming, large enough to matter. The structure does not get to rest. Living inside it is closer to living inside a submarine than living inside a house. Except the submarine analogy undersells it, because submarines surface. The habitat does not. The picture does not hold. The threat is not only the air you need, it is the ground beneath your feet. Martian soil looks like dirt. It behaves like something else. The regolith, the loose surface layer of dust and broken rock that covers most of Mars, is laced with perchlorates. Perchlorates are salts, and they are chemically aggressive. They disrupt thyroid function in humans. They increase cancer risk. They break down organic molecules. This means that raw Martian soil cannot be used directly for agriculture. It means that any dust that enters the habitat through an airlock, gets into the water supply, or contacts skin over months and years carries a chemical payload. Managing the dust is not a matter of wiping your boots. It is a continuous chemical decontamination project. Every EVA ends with an airlock procedure designed to strip off as much perchlorate-laden dust as possible before anyone brings it inside. And then, the storms arrive. A Martian dust storm can start as a local event and grow to cover the entire planet within days. Global storms have lasted weeks. Some have lasted months. The wind speeds are actually low by Earth standards because the air is thin, but the grains are ultrafine. They carry electrostatic charge. They work into seals and joints. They coat solar panels and reduce their output dramatically, sometimes for the full duration of the storm. They cloud sensors. They clog intake filters. They coat the radiators that shed excess heat from the habitat systems. The storms do not blow habitats over. That is the setup. Here is the reveal. They do not need to. They quietly degrade the power generation, the thermal management, the air filtration, and the communication systems, all at once, while making it the most dangerous possible time to go outside and fix anything. The storm does not attack. It simply sits there, reducing your margin, for weeks. This is the three-sided trap. The air is wrong, so you build machines to correct it. The soil is chemically hostile, so you manage every particle. The storms come and degrade the machines while preventing the repairs. You cannot step outside the trap. You have to live inside it. The only exit is to turn the trap into a tool. The Sabatier reaction takes carbon dioxide and hydrogen and produces methane and water. Electrolysis takes water and splits it into oxygen and hydrogen. Methane and oxygen together are a practical rocket fuel pair. The hostile, mostly carbon dioxide atmosphere that is trying to kill you is also, if you have enough power and the right machinery, a feedstock for propellant and breathing oxygen. In 2021, the MOXIE experiment aboard the Perseverance rover demonstrated this on the actual Martian surface. It pulled in Martian carbon dioxide and produced oxygen. The output was a few grams per session. Small. But the chemistry worked. On Mars. In the real thin air, at real Martian temperatures and pressure. Scaling that to colony-sustaining rates requires full chemical plants. Compressors, reactors, filter banks, storage tanks, pipelines, all running reliably for years through dust, cold, and the same thermal cycling that stresses the habitats. More machinery means more power demand. More power demand means more reactor or solar capacity. More components means more potential failure points. The solution generates its own new problem, not a dead end. A longer chain. And the air problem is only half the invisible load. The radiation comes constantly and in silence. There is no moment when it stops. Galactic cosmic rays, high-energy protons, and heavier atomic nuclei accelerated across the galaxy by supernovae and other violent events, pass through the thin Martian atmosphere the same way light passes through glass. Earth stops most of them. Earth has a thick atmosphere and a global magnetic field that deflects charged particles before they reach the surface. Mars has neither of those things anymore. The colonist under their meters of regolith is shielded. The colonist in a rover or a greenhouse or a transit module is not. The annual radiation dose on the Martian surface runs from 200 to 250 millisieverts per year. The Earth surface background is 2 to 3 millisieverts. The ratio is roughly 100 to 1. Every year on Mars without adequate shielding is the equivalent of many CT scans worth of accumulated dose, building on the year before it and the year before that. Stay with that. That sentence needs to land. A single CT scan of the abdomen is about 10 millisieverts. Mars surface exposure, unshielded, delivers that dose roughly 20 to 25 times over in a single year. The effects are not immediate. That is what makes radiation so difficult to think about. The colonist does not feel anything. They go about their day. The damage is in the DNA. in the cardiovascular tissue, in the developing nervous system. Cancer risk climbs, neurodegenerative risk climbs, cardiovascular risk climbs, and those risks are not equal for all ages. Children absorb more radiation dose per unit of mass. Fetuses are more vulnerable still. The same radiation environment that an adult might carry for decades becomes something more severe for any child born into it or conceived within it. Solar flares and coronal mass ejections add a different layer. These are bursts. A coronal mass ejection sends a wave of charged particles outward from the sun. On Earth, the magnetic field channels these toward the poles, and the result is an aurora. Beautiful, harmless at most latitudes. In deep space during the transit to Mars, or on the Martian surface during a major event, the same burst with thin shielding can deliver serious illness level or lethal doses in a single storm. The warning window from solar monitoring systems is hours, not days. When the alarm sounds, you stop what you're doing and you go to the shelter. The radiation shelter is a small space wrapped in mass. Water tanks overhead. Fuel stores around the walls. The heaviest available material positioned between the occupant and the incoming particles. Hydrogen-rich materials, water, certain plastics, liquid fuels are effective at slowing charged particles in ways that pure metal is not. This changes how vehicles, transit ships, and surface labs are designed from the ground up. Where you store the water determines how well the sleeping quarters are shielded. Where you store the food determines how safe the corridor is. The logistics map and the radiation map are the same document. For the chronic background exposure, the shielding answer is the planet itself. 2 to 3 meters of regolith overhead brings the dose toward manageable levels. This is why the early Martian city does not look like a city. It looks like a landscape with very little on it. The habitats are in trenches, covered over. The corridors are tunnels. The visible domes, if there are any, are facades. The real structure is out of sight, under the surface, where the rock is doing the work. For the human body carrying these exposures across a career, pharmaceutical interventions become part of daily life. DNA repair aids, dose tracking, limits on years in high exposure roles. And beyond those measures, the conversation has already begun about something larger. Tardigrades can survive radiation doses that would kill a human many times over. Deinococcus radiodurans, a bacterium, repairs its own shredded DNA with a speed and fidelity that has no human equivalent. Cockroaches absorb doses that dissolve human tissue and walk away. The human body was not designed for this environment. Every other organism in that list was shaped by billions of years of selective pressure. The Mars colonist has no such evolutionary preparation. The question that follows from that is not comfortable, and it is not settled. Whether gene editing can meaningfully extend human radiation tolerance, whether embryos can be designed with higher cancer resistance and more robust DNA repair machinery, whether the category of astronaut eventually becomes indistinguishable from the category of human engineered for Mars, none of that is resolved. All of it is being asked. What is clear is where the two invisible threats converge. The air problem and the radiation problem both arrive at the same destination by different routes. The body's exposure must be managed, shielded, controlled, or the body itself must change. The Martian environment does not negotiate. It simply continues, every hour of every day, doing what it has always done. And the hardest work on that planet has not yet been named. The body is already changing. That is what the radiation section makes clear. The cells are being altered. The DNA is accumulating damage, and the question of whether the human body must be redesigned to survive Mars has already been placed on the table. But radiation works on the invisible scale. It works at the level of molecules and chromosomes, years accumulating into decades. There is another force working on the body at the same time. It works at a larger scale, on bones and muscles and organs, and the geometry of the circulatory system. It works slowly and quietly, and it begins the moment the spacecraft leaves Earth. It is gravity, or rather, the absence of it. The human body has spent its entire evolutionary history inside a single gravity environment. 1G, not 0.8G, not 1.2 G. 1G continuously for every generation of every ancestor going back further than the species has a name. The body is not calibrated for that environment the way a machine is calibrated. It is built from it, shaped by it, dependent on it in ways that most of the body's systems never announce, because they never have to. Bone maintains its density because load demands it. Muscle holds its mass because movement in 1G requires it. The heart pumps blood upward against gravity dozens of times a minute, and the vascular system is tuned to that constant effort. The inner ear interprets what down means in a world where down never changes. The moment that changes, biology shifts. Not by choice, not gradually with warning, immediately, and in ways that are not fully reversible. The data from the International Space Station is where this becomes concrete. In microgravity, without heavy daily exercise, astronauts lose up to around 20% of their muscle mass in as few as 5 to 11 days. Not over months, days. The body reads the absence of load as a signal that the muscle is no longer needed, and it begins dismantling it. Bone density in the hips and spine drops at roughly 1 to 2% per month. To understand what that means, think about what osteoporosis does to a person over years. Then compress that same process into a single, long mission. That is what happens to the load-bearing skeleton in orbit. Fluid that normally pools in the legs under gravity shifts upward through the body, creating what astronauts call space face, a visible swelling of the head and face that goes with real physiological changes in fluid pressure around the optic nerve. The heart, no longer pushing blood upward against gravity, begins to shrink and reshape. Returning astronauts cannot always stand without assistance. Their balance systems have to relearn what down means. Their circulation has to relearn how to fight gravity. For some, that readjustment takes weeks. But that is microgravity. 0G. Mars is not 0G. Mars is 0.38G. And here is where it gets strange. No one has ever lived at 0.38G for an extended period. Not in any habitat, not in any experiment. The data we have is from 2 points on the curve. 1G on Earth, where the body is stable, and 0G in orbit, where the body degrades rapidly. Somewhere between those 2 points, there is a threshold. Below it, the body continues to weaken. Above it, the body stabilizes. We do not know where that threshold is. It might be 0.2G. It might be 0.5G. It might be somewhere uncomfortably close to 1G. Mars at 0.38G might sit safely above that threshold, or it might sit just below it. A colonist there would stay upright. They would feel weight. They would not float. But they might be losing bone and muscle at a slower rate than in orbit, continuously, for years. The first Mars crew is not going there to test this. They are going there to live, and they become the test. Every body system rebaselines at 0.38G. The heart no longer has to push blood as hard. The skeletal load drops to roughly 1/3 of what it is on Earth. The inner ear recalibrates to a new definition of down. For an adult who grew up at 1G, that rebaselining may be partial and painful. For a child who grows up at 0.38G, it is not a rebaselining at all. It is just normal. That is where the reveal lands. And it does not land comfortably. A child born on Mars does not experience 0.38G as a reduced version of something. They experience it as the only reality they have ever had. Their bones mineralize under the load they actually carry. Their muscles develop to match the forces they actually use. Their cardiovascular system tunes itself to the demands that are actually placed on it. The result may be a body that is not simply a weaker version of an Earth body. It may be a genuinely different structure. Longer, more slender limbs, altered proportions, a skeleton that is optimized for 0.38G and therefore structurally not adequate for 1G. Think about what that means concretely. A Martian-born child, raised, healthy, living a full life on Mars, might be physically unable to travel to Earth. Not unwilling, not economically prevented, physically unable. The cardiovascular strain of 1G might be too great. The spinal and joint loading might exceed what their frame was built for. Earth, for that child, would require rehabilitation, mechanical support, or possibly would simply be off limits. Mars would not be a colony sending humans home occasionally. It would be a place producing humans who are from Mars in a biological sense, not just a geographic one. There is no good analogy for what 0.38G does to a body across a full lifetime, because no body has ever experienced it. The closest approximation is something like growing up permanently in chest-deep water, where buoyancy reduces effective load and the musculoskeletal system develops to match a reduced demand. But even that analogy breaks down, because water does not change fluid dynamics in the chest and head the way partial gravity does. The honest answer is that we are generating the data in real time on real people, and the results will take generations to fully understand. The engineering community has an answer to this problem, at least in partial form. It is called a rotating habitat. A ring or drum that spins creates centripetal force on its floor surface, and that force behaves like gravity. Stand on the inside of a spinning ring, and you feel pressed outward toward the floor. Spin it at the right rate, and that outward force matches 1G. The physics is clean. The engineering is not. Larger radius means gentler spin needed to achieve the same force, which means less Coriolis effect on the occupants, but more material, more structural stress, more complexity in the joints that connect spinning sections to stationary ones. Smaller radius means more compact construction, but faster spin. And faster spin means Coriolis effects that are not subtle. Move your head quickly inside a rapidly rotating habitat, and the inner ear receives conflicting signals. The result can be disorientation, nausea, joint strain with repeated fast movements. Designing around Coriolis at small radius requires careful crew training and architectural choices about which movements are allowed where. The more likely design approach is not full artificial gravity across an entire habitat. It is something more targeted. Sleeping quarters and exercise areas built into spinning sections, rotating at close to 1G, so that the body gets its heaviest maintenance dose of real gravity during sleep and structured exercise. The rest of the base sits at Martian 0.38G. That means a colonist waking up in a 1G sleeping section, walking through a transition airlock, and spending their working day at 0.38G. 2 gravity regimes, 1 body, every single day. We do not know what the long-term physiological consequences of that alternation are. We know what each environment does in isolation, within the limits of available data. We do not know what daily switching between them produces over years. There is one more layer that has no clean solution. Long-duration spaceflight has introduced a condition called spaceflight-associated neuroocular syndrome, SANS, optic nerve swelling and flattening at the back of the eye, observed in astronauts after extended time in microgravity. The mechanism is related to fluid shifting upward in the absence of gravity and increasing pressure around the optic nerve. Some astronauts have returned with measurable, lasting changes to their vision. Whether 0.38G is enough to prevent that fluid shift, or whether Martian colonists develop similar ocular changes more slowly over years, is unknown. The circulatory system rebalanced to low gravity may also develop differently in ways that affect blood pressure regulation, cardiac geometry, and failure modes we cannot yet predict. Mental health may be coupled to gravity more directly than we realize, through sleep architecture, hormone cycles, and the way the brain spatially maps its own body in a gravitational field. We do not know how those systems behave across a life lived at 0.38G, and then the timescale extends further. 1 generation, 10 generations, 100. Natural selection does not pause because the environment is artificial. It acts on whatever variation exists, in whatever population is present. On Mars, the individuals whose bone chemistry is slightly more stable under low load live longer and reproduce more. The individuals whose DNA repair mechanisms are slightly more efficient under elevated radiation carry their children to term at higher rates. The individuals whose cardiovascular systems tolerate altered fluid dynamics more gracefully age more slowly. Over centuries, those small advantages compound. The population drifts, possibly toward higher natural bone density since the fragile individuals fared worse, possibly toward different cardiac geometry, possibly toward different birth weights, different growth rates, different lifespans, Add to that the trajectory of gene editing, which is already accelerating, and the trajectory of cybernetic integration, which is already beginning, and the line between a human who is from Mars and a human who is built for Mars starts to blur. Not as a metaphor, as a literal description of what the population becomes. The category Martian, over sufficient time, stops being geographic and starts being biological. That is the arc the gravity problem traces, from the first astronaut stepping off a transit ship with weakened legs, to a child who cannot visit Earth, to a population shaped by selection and technology into something the first colonists would recognize as human, but might not recognize as themselves. The gravity problem does not announce itself. It does not damage a seal or corrupt a system file. It simply works on the body, continuously, at the scale of years and generations. And the hardest part of it is that the deepest consequences will not be visible to the people who made the choice to go. But long before any of those generational changes can happen, the first colonists need walls that do not fail and air that does not run out. Think about what a building is on Earth. It keeps the rain off, it moderates the temperature, it gives you a place to be. That is the extent of what architecture has to do when the world outside is breathable and the pressure is stable and the temperature swings by 20 degrees between morning and evening. A wall on Earth is a weather barrier. A wall on Mars is a life support system. The pressure inside a Mars habitat runs somewhere in the range of 500 to 1,000 millibars. Depending on the design, the pressure outside is 6 to 7 millibars. That gap is enormous. It means the habitat shell is under continuous outward stress from the moment it is pressurized. Not stress like a dam holding back floodwater occasionally. Constant stress. Every weld, every seam, every window port, every gasket around every hatch is fighting that differential every hour of every day, year after year. The answer is stranger than expected. The external threat is not one thing. It is several things arriving from different directions at the same time. Micrometeorites are the first. The Martian atmosphere is thin enough that small particles are not fully slowed before they reach the surface. A grain of sand moving at several kilometers per second carries enough energy to punch through a thin metal wall. At those speeds, the grain does not bounce off. It passes through. So the habitat shell has to be layered. Real designs call for multi-layer composites, an outer armor layer to absorb or fragment the initial impact, a structural shell underneath, and an inner pressure bladder as the last line of containment. Some materials are engineered to swell or melt into small punctures on contact with the escaping gas, buying time. None of this is foolproof. It is a managed trade-off between protection, mass, and the cost of launching that mass off Earth. Thermal stress is the second. A single Martian day can swing from roughly negative 10 degrees Celsius, about 15 degrees Fahrenheit, in the afternoon to roughly negative 70 degrees Celsius, close to negative 95 degrees Fahrenheit, overnight. Every cycle, the habitat shell expands slightly in the warmth and contracts in the cold. Every joint, every seal, every valve experiences that flex daily. Over years, that mechanical repetition degrades materials in ways that are difficult to test in advance because no one has run a Mars habitat for decades yet. Managing that thermal swing means the habitat is not a building in any conventional sense. It is a thermal control system with living space attached. Radiators mounted on the outside dump waste heat generated by the humans inside, the electronics, the power systems, and the chemical machinery, dumping it into a thin atmosphere and a black sky. Insulation prevents the cold from creeping inward through the floor and walls. Pipes carrying fluids are routed carefully to avoid any section where they might freeze, crack, or overheat. Waste heat from nuclear reactors and large battery banks, which would otherwise be a problem to get rid of, becomes a resource. It warms the habitat interior, heats greenhouse sections, keeps water systems from freezing. Mismanage the balance and parts of the structure overheat, while other parts freeze. The residents live in the middle of a continuous thermal negotiation they mostly never see. Airlocks are where this becomes visceral. Every time a colonist needs to step outside, the airlock has to do industrial work. The inner door closes. Pumps pull the cabin air out of the lock chamber and store it, because venting pressurized, oxygen-rich air to the Martian atmosphere is wasteful and dangerous. Electrostatic systems strip Martian dust from the suit. Outer door opens. Every cycle stresses the seals on both doors, the hinges, the motors, the pump valves, and the pressure sensors. Every cycle risks dragging perchlorate-laced dust one step closer to the living volume. A well-designed airlock has multiple chambers and backup doors, so that a failure in one section does not immediately threaten the rest. EVAs are planned operations with checklists, scheduled when conditions are stable, not casual excursions. Now think about what happens when the colony grows. A single habitat module becomes 2, then 10, then 100. They cannot stand as freestanding structures separated by open ground. They have to connect. The result is a network of pressurized tunnels linking inflatable habitats, rigid cylinders, and structures printed from regolith, all joined by pressurized tunnels with bulkhead doors that can seal off any damaged section in seconds. Fire breaks are built into the layout from the first blueprint. Pressure zones are defined so that a single hull breach cannot decompress the entire city. Escape paths, safe rooms, medical modules, and power hubs are positioned so that isolated sections remain survivable while the breach is contained. A 1,000-person Mars city does not look like a town. It looks like a cluster of connected industrial plants, low and half-buried, with very little visible above ground, and the real structure extending downward and inward, where the regolith is doing the work. Building that cluster requires a material strategy that does not depend on shipping stone and steel from Earth. Regolith is the answer. Martian soil can be baked or melted into bricks without additives. Microwave sintering fuses the grains together using energy alone. No water or binders required. Mixing regolith with local ice or imported binding agents produces cements and concretes workable enough to print arches, domes, and vaulted chambers optimized for pressure containment. The geometry matters. An arch handles compressive load the way a submarine hull handles hydrostatic pressure, distributing force rather than concentrating it. Inside the regolith shells, inner pressure bladders or metal vessels handle the actual pressure containment, while the outer shell handles radiation and micrometeorite absorption. Over time, imported aluminum and steel become just the skeleton and the plumbing. The bulk of the city is local stone and ice. Shelter is only half the problem. The other half is everything the colonists consume and breathe every day, and that half runs as a continuous industrial process. On the International Space Station, water recycling operates at roughly 90% efficiency. That means roughly 10% of the water used aboard the station is lost and has to be resupplied. On Mars, resupply arrives on a 26-month cycle and carries a staggering cost per kilogram. A 10% loss rate is not acceptable. Mars needs better than 90%, significantly better, and it needs to sustain that rate for years, without the hardware degrading below threshold. The air loop is equally demanding. CO2 scrubbers pull carbon dioxide from cabin air using solid amine materials or similar absorbents that release the CO2 when heated, allowing it to be compressed and fed into reactors. Sabatier reactors, which combine that CO2 with hydrogen, produce methane and water. Electrolyzers then split the water into oxygen, which returns to the cabin air, and hydrogen, which feeds back into the Sabatier reactor or goes to storage as fuel and chemical feedstock. Every breath a colonist takes passes through this cycle. Every exhaled CO2 molecule is raw material. The system is a compact chemical plant running continuously inside the walls. But here is what the water supply chain actually looks like once you follow it to the beginning. Mars has ice. Polar caps hold thick deposits. Mid-latitude regions hold buried ice layers that radar and lander measurements have detected only a few meters below the surface in some locations, which makes those zones more practical for bases because the extreme cold of the poles is avoided. The extraction workflow is straightforward in concept. Locate the ice layer, drill or dig down to it, apply heat to drive it off as vapor or liquid, capture the outgassing, condense it, and store the result. In practice, every step requires powered equipment running in an environment that wants to freeze or crack that equipment. And the water that comes out is not clean. Not close to clean. Raw Martian ice carries dust, dissolved salts, and perchlorates at concentrations that are toxic to humans at sustained exposure. The purification train runs from mechanical filters to ion exchange resins to reverse osmosis or distillation for the harder contaminants. Each stage requires its own maintained hardware. Each stage produces a waste stream that has to go somewhere. The demand is not small. A crew of 10 needs roughly 30 to 50 litres per day just for drinking and cooking. Add hygiene, add irrigation for any plant systems, add the electrolysis process consuming water to produce oxygen, and total daily demand rises into the hundreds of litres, potentially exceeding 1,000 litres per day for a colony at any real scale. If the extraction rigs fall behind, the tanks start dropping, and operations change. The closed water loop also carries a biological risk. Warm, wet, closed systems are ideal environments for microbial growth. Organisms can colonize pipes and tanks. Chemical contaminants can build up in cycles if a filter media batch runs below specification. One undetected contamination event can move through the entire water supply before anyone knows it has happened. Constant lab testing for bacterial counts, chemical concentrations, and trace toxins is not a precaution. It is a core operational task. Oxygen production at colony scale cannot rest on small backup canisters. Emergency lithium hydroxide style scrubbers, the kind used on spacecraft and submarines to buy time during a system failure, are not a solution. They are a countdown clock. The solution is dedicated oxygen factories running electrolysis continuously, splitting water into hydrogen and oxygen at the kilogram per day scale required to sustain a living population. That scale of electrolysis requires serious power, which is why the connection between the power infrastructure and the life support infrastructure is not a preference, but a structural dependency. Fail the reactor, fail the oxygen. Oxygen lines, tanks, regulators, and valves are treated as serious industrial infrastructure because oxygen is reactive. A leak wastes a resource that cannot be easily replaced between resupply windows, and elevated oxygen concentrations in a closed space raise fire risk significantly. None of this machinery runs itself. Every pump, every filter housing, every compressor, every pipe joint, every pressure sensor must be maintainable by the people who live there using tools and spare parts already on Mars. Waiting 26 months for a replacement rotor is not a viable operational model. The design response is to limit the number of distinct part types, overbuild the critical items, stockpile seals and bearings and motor assemblies in sufficient quantity to cover multiple failures, and use 3D printers fed with local feedstock to produce brackets, casings, and simple structural parts on demand. When a choice exists between a high-efficiency delicate system and a low-efficiency robust one, the robust one wins if the delicate one cannot be repaired locally. The colonists need systems that can limp, not systems that run perfectly until they fail completely. The closed loop is mechanical and industrial as much as it is chemical, and keeping it closed every hour of every day, with the tools that are present and the people who are available, is the work that makes everything else possible. The deepest constraints on that work are still ahead. Air and water are not the only things that have to keep running. The food does not stop, and the power that grows it does not stop either. Start with the simplest framing. Feeding people on Mars is not a gardening problem, it is a numbers problem. Each person needs somewhere between 2,000 and 3,000 kilocalories per day. For a crew of 10, that is 20,000 to 30,000 kilocalories required every single day, with 0 missed days across years, with no grocery shipment coming on the next rocket. The planning metric is not harvest weight. It is calories per square meter per year for each crop type under Martian conditions. Every square meter of growing space costs floor area, structural mass, and power. Every crop choice is a trade-off between growth speed and caloric density. Leafy greens grow fast but carry few calories. Potatoes, wheat, and beans grow slower, but delivered the dense energy that keeps bodies working. A realistic colony grows both in multi-layer vertical racks, stacking growing surfaces one above another to squeeze more yield from limited pressurized floor area. Here is where the first setup collapses. Mars has surface material. It looks like soil. It is not soil. It is crushed rock, glassy mineral fragments, and chemically active dust with almost no organic content. It also carries perchlorates, chlorine-based compounds that are toxic to humans and that break down organic molecules. You cannot plant in it, not without removing those toxins first, which requires washing and baking large volumes of regolith at significant energy cost. The simpler path, and the one most serious Mars agriculture proposals follow, is to skip the regolith entirely. The alternative is hydroponics and aeroponics. Hydroponics suspends plant roots in flowing nutrient solution. Aeroponics suspends them in air and delivers nutrients as a fine mist. Both require fertilizer salt tanks, pumps, tubing, filters, and continuous sensor monitoring of pH levels, nutrient concentration, dissolved oxygen content, and trace element balance. Both require LED lighting tuned specifically to the red and blue wavelengths that plants use most efficiently. Because full spectrum light wastes energy on wavelengths plant chemistry mostly ignores. The greenhouse is not a garden. It is a liquid-based factory where plants are the machines and kilocalories are the product. That framing matters because factories can fail. A pump stops. A nutrient line blocks. Someone miscalibrates the mineral mix. In a terrestrial greenhouse, you have time to notice and respond. In a sealed Martian greenhouse where the entire colony's calorie supply is running through those pipes, a failed pump can begin killing rows within hours. The margin is thin. The monitoring requirements are continuous. Sunlight adds another layer to the problem. Mars receives roughly 43% of the solar energy Earth does at the same angle. Before any dust arrives, dust storms reduce that further, and during a global dust event, surface sunlight can fall by more than half for weeks at a time. Two approaches exist. One is large translucent greenhouse structures combined with mirrors, and robotic dust cleaning systems that keep the glazing clear enough to pass useful light. The other is fully enclosed farms where high-efficiency LEDs provide most or all of the light, replacing the sun entirely inside the growing space. A real colony will use both, but the implication is the same either way. Every lumen replaced with LED output costs power. Agriculture is an energy equation, watts in, calories out. A dust storm does not just threaten the solar panels, it threatens the calorie pipeline directly, unless stored energy can cover the gap. Plants also cannot function alone. On Earth, crops grow inside complex communities of bacteria and fungi that live in and around the root systems, break down nutrients into forms roots can absorb, and suppress pathogens. Soil delivers those communities for free. A sealed Martian greenhouse inherits nothing. The colony must deliberately cultivate and introduce beneficial microbial populations and then monitor them continuously. Something else is happening. A sealed greenhouse is also a perfect environment for the wrong organisms. One invasive mold, one plant pathogen, one wrong strain of algae introduced into a nutrient tank can spread through a closed air and water system faster than in any open field. The farming team is not just a team of farmers, they are microbiologists running regular sampling of water, roots, and leaf surfaces, tracking microbial populations the way an immunologist tracks cell counts, and maintaining sterilization protocols that can reset a contaminated section without destroying the rest of the greenhouse. Survival calories solve the physiological problem. They do not solve the human one. Bland staple-only diets erode morale over months. Once the basic calorie budget is stable, the colony begins growing coffee, herbs, spices, small fruiting plants, anything that adds variety and sensory pleasure to the food supply. Yeast for bread, for beer, for fermentation. Cultured meat grown from cell lines in bioreactors, producing animal protein without animals. Each addition costs space, water, energy, and labor. Each addition is worth it for reasons that do not show up in caloric accounting. The day fresh bread comes out of an oven from wheat grown under the colony's own lights is not an agricultural milestone. It is the moment life on Mars crosses a threshold, from survival into something that begins to resemble a civilization. Underneath every part of that picture is the same infrastructure. Every pump, every LED array, every fan, every filter, every sensor runs on power, which means that feeding the colony is inseparable from powering the colony. On Mars, power is not about convenience. It is the line between a functioning life support system and a frozen habitat where everything that was keeping people alive has stopped. Solar panels are the obvious starting point. No moving parts, no fuel, just surface area and sunlight. But solar on Mars means 43% of Earth's intensity before the dust touches anything. Dust settling onto panel surfaces reduces output further, day by day, until a large array that looks sufficient on day 1 is producing a fraction of its rated capacity on day 100. Keeping panels producing at rated output requires robotic cleaning systems, mechanical brushes, gas jets, electrostatic shakers, or tilting mounts that shed accumulated dust. And a global dust storm can cut surface sunlight by more than half for weeks. Precisely when sending crews outside to service the cleaning systems is most dangerous. A colony drawing hundreds of kilowatts continuously, which is what life support, lighting, heating, and agriculture require at even modest scale, needs battery storage in the megawatt-hour range to ride through nights and storm periods. That is roughly equivalent to the storage capacity needed to keep a small town running, built from hardened versions of the battery packs inside electric vehicles, designed to survive Martian cold and low pressure. Heavy, degrading over time, difficult to replace. Every new person, every new greenhouse module, every new workshop adds load. Solar alone is too fragile to carry a colony that cannot afford to have the power fail. Nuclear fills that gap. Small fission reactors in the kilopower class, designed to run continuously for years, produce around 10 kilowatts each. 10 of those running together produces roughly 100 kilowatts. Scaling further into the megawatt regime provides enough reliable power for life support, labs, machine shops, farms, and the beginnings of industrial production. Nuclear is weather independent. A reactor does not notice a dust storm. It does not dim at night. But nuclear on Mars carries its own engineering load. Reactors must be positioned far enough from habitats to limit radiation exposure, buried or shielded with regolith piled around them, and designed for long-term fuel management without support from Earth. Leak tracking, spent core handling, and no external regulator, no off-site emergency response team, no national grid to fall back on if something goes wrong. Engineering standards and operational discipline are the entire safety system. A reactor problem on Mars is not a regulatory incident. It is a mission-threatening emergency. Batteries alone cannot bridge all the gaps between generation and demand. The layered storage strategy adds 2 more options. Chemical storage runs surplus power through electrolyzers, splitting water into hydrogen and oxygen that can be stored in high-pressure tanks and fed back into fuel cells during shortfalls. Less efficient than using power directly, but capable of buying hours or days of backup during a crisis. Thermal storage uses surplus electricity to heat large masses of rock, regolith, or molten salt, then draws that stored heat back later to warm habitats or industrial processes. A thermal battery, in the same way a water tank is a pressure battery. Every watt-hour that can be shifted from a time of surplus to a time of shortage is 1 more unit of margin when something breaks. Distribution ties the system together, not overhead poles and utility lines, but cables running through tunnels and conduits buried under regolith, connecting generation sources to storage banks to habitat loads. High-power DC lines suit the architecture well, since solar panels, batteries, and modern electronics all work more naturally with direct current. Solid-state switches reroute power automatically when a line trips. Critical cable paths are duplicated, so a single severed connection does not cut power to a life support module. Software becomes part of the life support stack. Smart load-shedding algorithms run continuously. monitoring total generation and total demand, and deciding in milliseconds what to cut if supply drops. The priority stack is fixed. Air pumps, CO2 scrubbers, water recyclers, and medical gear sit at the top. Non-critical lighting, secondary laboratories, and manufacturing processes sit below. A bug in that software is not an inconvenience. A bug in that software is a cascade into life-threatening failure. Civilization has a metabolic rate. On Earth, each person in a developed country uses thousands of watts continuously when you account for the industry, transport, data infrastructure, and heating that supports their daily life, the equivalent of dozens of electric kettles running without pause. On Mars, energy is not a utility cost. It is a hard cap on everything. On population, on industry, on emergency buffer. A colony with 5 megawatts of reliable generation has a corresponding ceiling on how many people it can support, how many greenhouses it can run, and how much margin it has when something fails. 100 more settlers does not mean more seats on a rocket. It means more reactors, more solar panels, more storage banks, more cables, more inverters, more maintenance crews to keep all of it running. Energy growth and population growth are the same project. Store the energy system and everything else stores with it. The calorie supply and the power supply are not two separate problems. They are the same problem stated twice, and solving them is the infrastructure that makes everything else the colony does possible. And once there is enough power, the question becomes what to do with it. The smelters come first. The colony has been running on Earth cargo since the first crew landed, unpacking crates, rationing every spare part, treating every bolt as irreplaceable. That works for a year, maybe 2. But a colony that depends entirely on Earth shipments is not a colony. It is a campsite. Real survival requires something different. It requires treating Mars as what it actually is. A raw material dump, frozen into the rock and thin air, waiting to be processed. Martian regolith is not clean soil, and it is not empty stone. It contains iron, aluminum, silicon, magnesium, and sulfur, among other elements. The challenge is liberating them. Smelting iron requires furnace temperatures above 1000 degrees Celsius. Refining aluminum requires high-temperature electrolysis, splitting compounds apart using electrical current the way the life support system splits water into hydrogen and oxygen. Producing usable silicon for glass or solar cells requires its own chain of chemical steps, all calibrated for low atmospheric pressure. The first factory on Mars is a cluster of rugged modules, a smelter, a kiln for turning regolith into glass, an electrolysis line for separating elements. It does not look like anything from Earth's industrial zones. It looks like the inside of a submarine crossed with a chemistry lab, but what comes out of it is real. Iron for beams and tools, aluminum for structural frames, silicon for windows and panels. Every ton produced locally is 1 ton that did not have to be launched from Earth's gravity well. Think about what that means for the supply chain. The cost per kilogram to Mars' surface runs into the tens of thousands of dollars. A single structural beam fabricated on Mars from local ore cost the colony a fraction of what the same beam would cost delivered from Earth. Over years, local production is not an efficiency gain. It is the difference between a colony that can grow and one that slowly runs out of room to breathe. Then the picture shifts. The smelters and kilns are only the beginning of what the factory does. When a valve body cracks, a traditional colony waits for the next supply window. That is potentially 2 years away. A colony with a working 3D printer loads a design file and produces the replacement part in hours. On Mars, 3D printing is not a novelty. It is survival infrastructure. Multiple printer types run in parallel. One for plastics, one for metal powders, one using regolith-derived feedstock for structural components. As local ores are refined into alloys and powders, the line between the mine and the factory blurs. The mine feeds the refinery. The refinery feeds the printer. The printer produces wrenches, pipe joints, housings, structural connectors, and eventually parts of new printers. The loop closes. The colony becomes less dependent on Earth with every operational month. And then the fuel plant changes the strategic picture entirely. Methane and oxygen are the practical propellant pair for Mars because both are makeable from materials that exist there in abundance. The chain runs like this. The atmosphere is nearly pure carbon dioxide. Subsurface ice is drilled and melted into water. Electrolysis splits the water into hydrogen and oxygen. The Sabatier reaction, a well-understood chemical process, combines that hydrogen with carbon dioxide from the atmosphere to produce methane and water. The water loops back to the electrolyzer. The methane and oxygen are stored as propellant. At small scale, this fuels rovers, generators, and shore-hop surface vehicles. At large scale, producing hundreds of tons per launch window, something else happens. Mars stops being a destination. It becomes a fueling stop. A heavy spacecraft can arrive at Mars mostly empty of propellant, having used minimal fuel for the descent, and refuel entirely from local production before departing toward the asteroid belt or the outer planets. The difference between a stranded outpost and a hub for outer system missions is not a technology that needs to be invented. It is a chemical plant that needs to be built and run. The colony that solves its own fuel supply becomes a different kind of place in the solar system. The chemical plants do more than make fuel. They are survival organs. Plastics for habitat seals, pipe fittings, and cable insulation all trace back to chemical feedstocks. The fertilizers that keep the hydroponic farms producing, the nitrogen compounds, phosphorus, potassium, and trace elements are processed by industrial chemistry. Solvents for cleaning and manufacturing, refrigerants for cooling systems, pharmaceuticals for the clinic. All of it runs through reactors, distillation columns, and catalyst beds that must be maintained continuously under high temperature and high pressure, with tight control over every pump and valve. A chemical plant stall is not an economic problem. It is a health and survival event. Fertilizer production slows, crop yields drop, plastic output stops, and there are no replacement seals or gaskets. The drug supply runs down with no quick restock. The consequences move through the colony like a slow pressure drop, not immediately catastrophic, but narrowing every margin. And running through all of it, corroding everything it touches, is the dust. Martian dust particles are fine enough to infiltrate bearings, seals, intake filters, optical sensors, and electrical contacts. They carry electrostatic charge that makes them cling to surfaces rather than settle. The design responses are real. Positive pressure housings that push clean air outward through seals so dust cannot enter. Layered serviceable filters that can be replaced before they fail. Bearings and lubricants engineered to tolerate contamination that would destroy standard machinery. Even so, equipment lifespan on Mars runs shorter than Earth norms. Motors burn out faster, seals wear sooner, pumps and fans need more frequent overhauls. Spare part demand runs higher than any Earth engineer reviewing the original specifications would feel comfortable with. Mars is constantly trying to sand the edges off the civilization being built there. Chemical erosion and mechanical erosion working together, patient and relentless. This is where the robots become non-negotiable. Human EVA time on Mars is rare, slow, and dangerous. A suited colonist working outside for a few hours represents a significant expenditure of preparation time, suit wear, airlock cycles, radiation exposure, and physiological cost. Running the smelters, cleaning the panels, inspecting the reactor shielding, maintaining the fuel plant, patching the exterior walls. No human crew is large enough to do all of that manually, even if the suits allowed it. Without machines doing most of the work, the colony plan collapses under its own operational load. The autonomy problem bites immediately. The one-way signal delay between Earth and Mars runs from several minutes at closest approach to more than 20 minutes when the planets are far apart. Real-time remote control is impossible. Think about driving a remote control car with a 20-minute lag between moving the joystick and the car responding. By the time you see the obstacle on the camera feed and move to correct, the rover has already hit it, stopped, and been sitting there waiting for new instructions for half an hour. That framing feels like an exaggeration until you actually run the numbers. It is not an exaggeration. Control shifts to high-level instructions. Go from point A to point B. Scan the area. Avoid obstacles. Collect samples. Report back. The rover must see the rock in its path, plan an alternate route, handle the unexpected rut or soft patch, and recover if it gets mildly stuck, all without a human in the loop. A robot that cannot self-recover from a minor setback becomes a liability on a planet where survival-critical tasks are waiting. Before the first human crew arrives, robots are the construction crew. They dig trenches for power cables and pipes. They level landing zones and pile regolith into radiation-shielding berms. They 3D print bricks from sintered regolith and prospect for ice deposits, mapping depth and purity. All of that work is finished, or supposed to be finished, before any crew steps off a lander. If the construction bots fail, the arriving crew finds a half-built base. Their first month becomes emergency robot repair instead of habitat setup. Once humans arrive, more work goes to robots, not less. Small maintenance bots crawl through tunnel networks, checking seals, scanning for corrosion, clearing filters, and moving containers. Outside, swarms of semi-disposable machines clean solar panels, inspect reactor shielding, climb communications towers, and scan for micrometeorite damage. If one dies, send another. The cost is a fraction of a human EVA. Colony health becomes a function of how many tasks can be pushed to machines that do not care about radiation, cold, or the monotony of running the same inspection circuit for the 400th time. The AI layer runs underneath all of it. The sensor density of a Mars base exceeds anything a human crew can monitor continuously. Pressure readings, temperature gradients, flow rates, power draw, chemical concentrations, radiation flux, structural strain. No team of engineers, however alert, can track all of it simultaneously. The AI watches for patterns. A pump drawing slightly more current than its baseline. A CO2 scrubber regenerating more often than expected. A slow drift in oxygen purity, or a gradual shift in water pH. These are not alarms yet. They are early signals, the kind a doctor reads in an EKG before any symptoms appear, before the patient feels anything wrong at all. The AI flags them hours or days before they escalate, suggests a filter change, reschedules a power-intensive process, reroutes a valve. The difference between catching a scrubber problem early and missing it until it matters is not a minor operational distinction. It is the difference between a filter swap and a base-wide carbon dioxide emergency with hours of breathable air remaining. But the trust problem has no clean answer. The colony is betting its life on code the colonists did not write. Running on machines, they cannot always open and inspect. How much autonomy is safe to grant? Can the AI shut down part of the power grid if it detects an overheating risk without asking anyone first? Can it reroute power away from a science lab to protect life support automatically in the middle of the night? What if it accepts a brief stress on one power line to stabilize the system overall, but does not explain its reasoning clearly enough for anyone to verify it made the right call? Guardrails exist. Critical decisions require human confirmation. Independent checks run in parallel. Manual overrides are always available, but complexity grows. In a fast emergency, waiting for a human vote costs time the system may not have. In a slow trend, dismissing an AI prediction because it is just a model can be catastrophic. Over time, the line shifts, not by policy, not by design intention, but by operational reality pressing against it every day. The colony becomes something that has no exact name. Robots handle the surface, bots handle the interior. AI handles prediction, coordination, and optimization. The colonists design tasks, make strategic decisions, and repair what breaks. Each of them is no longer simply a person working on a planet. Each of them is part of an organism made of people, metal, code, and rock. And the hardest questions about how that organism should make decisions in a crisis are still ahead. Those hard questions about decision-making lead somewhere the engineering diagrams do not show. They lead to the people inside the organism. The bodies and minds that all of that metal and code exists to keep alive, and they turn out to be the hardest system of all. On Mars, every medical problem is the colony's problem. Not one person's problem, not a family's problem. The colonies. There is no emergency flight to Earth, no helicopter, no off-site trauma center down the road. An evacuation to Earth takes months, and any critically ill patient would almost certainly not survive the journey. The base must carry its own full hospital, because the only alternative is to carry no hospital at all. That means an operating room capable of real surgery, appendectomies, fracture repair, emergency C-sections, wound closure from industrial accidents. It means imaging equipment, ultrasound at minimum, possibly a compact CT scanner if the mass and power budgets allow. It means blood storage, transfusion capability, ventilators, sterilization systems, monitoring equipment, a deep and broad pharmacy covering painkillers, antibiotics, antivirals, anticoagulants, blood pressure medications, psychiatric drugs, allergy treatments, and emergency drugs for shock and anaphylaxis. Sutures, dressings, catheters, IV lines, gloves, masks. The local staff must be able to handle broken bones, severe industrial burns, chemical exposures from the processing plants, and chronic conditions like diabetes or respiratory disease. Urgent care on Mars is a planetary question. Can this base, right now, handle this case? There is no other answer available. That is where the pattern breaks. Mars does not simply make familiar medicine harder. It creates conditions that have never existed in a clinical setting before. Colonists will breathe recycled air in close contact with Martian dust. That dust carries perchlorates, the same chemicals that contaminate the regolith and complicate agriculture. Inhaled over years, it is likely to cause chronic irritation, asthma-like symptoms, and possibly novel lung diseases that match nothing in any Earth pulmonary atlas. The chronic low-level radiation discussed in earlier sections does not merely add cancer risk in a general sense. It may shift which cancers dominate. Leukemias, brain tumors, malignancies that appear at frequencies and in patterns that Earth oncology databases were never built to predict. The colony will also develop its own microbiome, the ecosystem of microorganisms living in and around the colonists. Human bacteria and fungi from the crew will mix with organisms introduced on equipment, and with species that find warm, moist niches in the life support infrastructure. Biofilms will form in water lines, filters, and condensers. Under the combined pressure of radiation and stress, microbes can evolve rapidly, swapping genes through a process called horizontal gene transfer, where bacteria pass genetic material directly to each other, rather than through reproduction. The result may be unusual pathogens or unusual behaviors in otherwise harmless organisms, producing infections or immune responses that Earth medicine has no case history for. Add to all of that the permanent background stress of living in a sealed environment where any minor failure is potentially lethal, and the medical literature on Antarctic winter, overcrews, and submarine deployments predicts elevated rates of anxiety, depression, sleep disorders, and stress-linked immune problems as near certainties, not possibilities. The clinic on Mars is also a research laboratory. Every strange infection, every anomalous tumor, every symptom cluster that does not match a known diagnosis must be documented and studied. Treatment protocols will be adapted with tiny sample sizes, often with no comparable cases anywhere in the literature. For some of what happens in that clinic, the colony will be writing the first case reports in human history. Earth consultations are possible, but ask anyone who has ever waited a day for a letter to arrive with a doctor's reply, and they will tell you the limits of that system. When a specialist on Earth reviews a patient's scans and vital signs and sends back a diagnosis, the advice may return in an hour or the next day, depending on where Mars sits in its orbit. For chronic care and planned procedures, that is workable. For active bleeding, a seizure, or a cardiac arrest, the advice arrives long after the window has closed. The local team handles it. Local generalists trained across emergency medicine, basic surgery, internal medicine, pediatrics, and mental health. AI decision support systems that flag probable diagnoses, suggest drug doses, and check for dangerous drug interactions. But the final call is local. It is always local. The supply problem compounds this. Rare medications or specific implants may be 2 launch windows away, which means roughly 2 years. That gap changes how medicine is practiced. Broad-spectrum tools replace specialized ones. Antibiotics chosen to work against a wide range of bacteria rather than a single target organism. Multi-use surgical instruments instead of procedure-specific hardware. 3-dimensional printed prosthetics and braces instead of custom medical devices shipped from Earth. Equipment that would be discarded after a single use on Earth gets sterilized and used again. And there is the drug shelf life problem. Medications expire. A pharmacy cannot simply hold its stock indefinitely while waiting for the next resupply. The solution the colony needs is on-site pharmaceutical manufacture. Bioreactors, fermentation vessels containing engineered microorganisms, bacteria or yeast, or in some cases mammalian cell lines, can produce insulin, certain antibiotics, vaccines, hormones, and clotting factors directly on Mars. The supporting infrastructure is real and buildable. Fermenters, purification units called chromatography columns that separate the target compound from everything else in the fermentation broth, and sterile filling lines to package the result. This breaks a deep assumption about medicine. High-end pharmaceutical production is not confined to large Earth hospitals and industrial drug plants. It can live in a Mars base if the base is designed from the beginning to hold it. Then comes the question that no medical textbook has addressed. What does a Martian pregnancy look like? Nobody knows. The first birth on Mars is a high-stakes experiment with no precedent. The effects of 0.38 times Earth's gravity on fetal growth, bone formation, organ development, and brain wiring are genuinely unknown. The pediatric medicine that follows is equally uncharted. Martian-born children will develop bones that mineralize under lower gravity, muscles and joints adapted to easier movement, vestibular systems and brains calibrated to a weaker sense of down. Growth charts built from Earth data do not apply. Motor milestones developed from Earth observations do not apply. New normal ranges will have to be established from scratch, from real children as they grow. Aging on Mars will produce different fracture risks, different cardiovascular loads, different cancer patterns shaped by earlier and higher cumulative radiation exposure than any Earth population has experienced. Rehabilitation after injury or illness looks different under weaker gravity. Earth-developed physical therapy protocols do not translate cleanly. Mars medicine is not familiar problems made harder by difficult conditions. It is the rewriting of the medical rulebook from first principles in real time, while real people live and die under the rules being written. Every treatment, every birth, every long-term survivor contributes to a new picture of what a human body can become when Earth is no longer home. And the body is only the beginning. The mind operates inside the same sealed environment. The Mars environment never stops signaling danger. Tight corridors, machines whose failure means death, a lethal exterior on the other side of every wall, no genuine break from the background awareness that any moment could be the moment something goes wrong. Antarctic winter overcrews experience elevated rates of depression, anxiety, sleep disruption, and interpersonal conflict, even with training and preparation. So do submarine crews. Those situations have known time limits. A submarine surfaces. A winter over station ends. They also have vastly shorter distances to home. Mars adds higher stakes, greater distance, and no visible endpoint to the isolation. The psychological pressure is not a side effect of living there. It is a structural feature of the environment. Mental health support, in response, is not optional infrastructure. It is not the kind of thing a colony builds once it is comfortable. It is core life support, on equal footing with oxygen monitoring. This means private space for every colonist, even if that space is small. Scheduled downtime that is genuinely protected from mission creep. Psychologists, counselors, and peer support systems operating from the first day the colony is occupied. Sleep patterns, mood states, and stress markers monitored with the same regularity as CO2 concentrations and pressure readings. Without this, burnout builds, bad decisions accumulate, conflicts escalate into safety threats. A personal crisis in a sealed colony does not stay personal for long. The communication delay reshapes more than emergency medicine. 4 to 24 minutes one way means no live shared experiences with Earth. No shared news, no real-time conversation, no watching the same event together and reacting in the same moment. Messages arrive in bursts. Over years, the colony's relationship to Earth begins to drift. Not dramatically at first. Slang develops, inside references accumulate, risk attitudes shift to match the local reality rather than the one preserved in delayed video messages from Earth. Local milestones become the calendar that matters. The date the base became operational, the first successful harvest, the first dust storm that passed without casualties. A Mars-born child will feel the connection to neighbors in the next corridor more vividly than the connection to a relative on another planet sending messages that arrive a day late. The question that begins as a philosophical curiosity becomes practical quickly. Are the colonists part of humanity, or are they becoming something distinct? Are they employees of Earth organizations, or residents of a place with its own interests? The answer to that question requires law, and there is currently almost none. Space law as it exists focuses on nations, satellites, and the principle that no country can claim sovereignty over a celestial body. It does not address how to run a city on another planet. Mars must invent from scratch. Criminal law that accounts for the fact that sabotage or serious carelessness can kill every person in the colony, not merely the immediate victim. Property law settling who can own a habitat module, a reactor, a patch of regolith, a pocket of extracted ice. Labor law defining working hours, hazard pay, and the rotation between high-risk and lower-risk assignments. Environmental rules governing what can be vented outside, what brine can be dumped, how ice deposits can be disturbed. Emergency powers establishing who can override normal rules during a crisis, whether a commander can order someone into an EVA they refuse, and whether the organization financing the colony owns colonist labor for a fixed term, or whether colonists hold something closer to citizenship. The edge cases test every concept. Deliberate sabotage of life support equipment. Is that vandalism, attempted murder, or terrorism? A colonist refusing medically necessary quarantine during an outbreak, knowing the refusal endangers everyone. What enforcement exists, and who applies it? Every legal concept from Earth bends and sometimes breaks when small infractions can cascade into colony-wide emergencies. Culture lives in the same space as law, and it does the same kind of work. A handmade guitar assembled from limited materials. Flowers growing in a corner of the greenhouse. Weekly low-gravity movie nights in a common area. A wall painted with an image of Earth. A poem written after the colony's first survived dust storm. Ceremonies held for the people who were lost. These are not comforts added once survival is secured. They are pressure release valves. They let people talk about fear obliquely, laugh at what is genuinely frightening, and build an identity that extends beyond the daily work of keeping the systems running. New art forms will emerge from the constraints. Instruments built to be as light as possible. Digital performances streamed through the colony network. Virtual reality environments, simulating open skies that no one inside can see directly. Culture provides the vocabulary for fear. It builds something to belong to beyond a shared maintenance schedule. Conflict arrives regardless. On Earth, the unhappy options include walking away, leaving a bad workplace, or moving to a different city. On Mars, the social universe is dozens to a few hundred people. Daily contact in corridors, in shared meals, in emergencies. Two people with serious animosity between them may need to share an airlock. They may need to trust each other during a suit failure. Groups that disagree on a major decision cannot separate into different neighborhoods. Formal systems are required. Structured mediation, clear grievance procedures, rotating assignments that reduce chronic friction by changing who works alongside whom. Transparent governance of work rotations and resource allocation, because perceived unfairness in who takes the high-risk jobs erodes trust faster than almost any other single factor. Personal ego must sit beneath mission safety. That is not a natural state for most people. Colonists will still be angry, jealous, frustrated, grieving. The difference from Earth is the consequence. Unchecked conflict in a sealed colony does not stay between two people. It becomes equipment sabotage, unsafe shortcuts, refusal to cooperate during a crisis. A personal breakdown on Mars carries group consequences faster than any equivalent breakdown on Earth. If mental health fails, people break. If law fails, trust breaks. If culture fails, motivation and cohesion break. Any one of those failures makes every technical problem the colony faces significantly harder to solve. The soft systems are not soft, they are load-bearing, and the work of building them begins before the first rocket leaves the ground. All of that holds. The soft systems carry the colony the same way the physical ones do, but pull back far enough from the daily arithmetic of oxygen and calories and conflict. And a larger question comes into view. What is all of this actually building toward? The popular answer to that question goes something like this. We go to Mars, we set up a base, and eventually we do what humans have always done to new places. We change the environment to suit us. We thaw the poles, pump some gases into the air, warm the planet up, and one day someone walks outside in a light jacket and breathes freely under a blue sky. That is the vision. And the numbers do not support it. Here is what the math actually says. Earth's atmosphere has a mass of roughly 10 to the power of 18 kilograms. Written out, that is a billion kilograms of gas held down by Earth's gravity, giving us the pressure we breathe, the temperatures we tolerate, and the ultraviolet shielding we need. Mars currently runs below 1% of Earth's surface pressure. The gap is not a rounding error. It is almost the entire distance. The standard terraforming plan involves releasing all available carbon dioxide locked into the Martian polar caps and regolith, the loose broken rock covering the surface. When researchers actually inventory what is available, the shortfall is severe. Even under the most optimistic assumptions, fully releasing all that stored carbon dioxide would produce a pressure that still requires a pressure suit and an oxygen mask to survive. Not comfortably thin. Still lethally thin, just less so. But the inventory problem is not the worst of it. Even if you solve the inventory problem entirely, by importing volatiles from icy moons, or nudging comets into Mars-crossing orbits to dump fresh atmosphere onto the surface, Mars would erase it. Mars lacks a strong global magnetic field. Earth's magnetic field deflects the solar wind, the constant stream of charged particles flowing outward from the sun. Mars lost its global field billions of years ago. Without it, the solar wind strips atmosphere away, particle by particle, year after year. Mars has been losing its air for billions of years already. That is why it is so thin now. Thickening the atmosphere does not solve this. A thicker atmosphere is simply a larger target for the same stripping process. Terraforming is not a one-time installation. It is permanent planetary scale maintenance, sustained across centuries with no guarantee of outrunning the loss mechanisms. More aggressive proposals exist. Engineers have sketched out engineered super greenhouse gases, molecules designed to trap far more heat per molecule than carbon dioxide. Some candidates break down under ultraviolet radiation or atmospheric chemistry within years or decades, requiring continuous industrial production to maintain concentration. Others suggest nuclear detonations over the polar caps to release stored carbon dioxide quickly. The headline lands well. The energy mathematics are brutal. Warming an entire planet requires sustained energy input on the order of total human civilization's output. Directed at a single target, over timescales no current civilization has ever maintained anything. Mars compounds the problem at every turn. Small mass, lower gravity, farther from the sun, and a thin atmosphere that radiates heat away efficiently rather than holding it. Mars works against the project at every level. Full terraforming is a multi-millennium commitment with no guarantee of arriving anywhere. Then the data shifts. The realistic path, the one achievable within centuries rather than geological time, does not involve changing Mars at all. It involves building pockets of Earth-like conditions inside Mars, as it is. The concept has a name: para-terraforming, not changing the planet, building sealed environments on the planet where the planet's conditions are irrelevant to the people living inside them. Domes over craters, pressurized roofs spanning canyon floors, tunnel networks running beneath regolith hills, topped with translucent shells. Inside these structures, pressure is controlled, gas mix is controlled, temperature and humidity are controlled, mirrors concentrate and filter sunlight, enclosed structures run on artificial light. Outside, Mars stays Mars. Red, cold, nearly airless, stripped by the solar wind. Inside, you walk in a shirt. Trees grow. Small ponds collect condensed water. Streets are crossable without a suit. The engineering scale is significant. Kilometer-scale roofs require massive structural supports and building-sized airlocks. But the controlled volume is local, not planetary. You are not rewriting the sky above a hemisphere. You are building a town under a roof. Thousands of these structures, grown over generations, give practical habitable zones to millions of people without touching the atmosphere above them. And this is where the deeper shift happens, the one that matters more than the engineering. A person born on Mars, raised under a dome, looking out at a red sky through a transparent wall, does not experience that sky as wrong. It is simply the sky. The gravity pulling at 0.38 of Earth's standard is not deficient gravity. It is the gravity they have always known. Over generations, the aesthetic of home shifts with the environment. Decorations in a Martian habitat may not simulate an Earth copy. They may celebrate the dust patterns on the outer walls after a storm, or the particular way light bends through a frozen regolith lens in winter. The fastest path to a livable Mars is not planetary weather control. It is local engineering, combined with biological adaptation and cultural adaptation running in parallel. The story changes, not clone Earth. Survive and thrive as a multi-planet species in genuinely different conditions. That reframe matters, because it changes what the whole project is actually for. Every human alive right now lives on one planet, wrapped in a thin shell of air and water. Roughly 8 billion people. One point of failure. Earth's own history makes the stakes clear. This planet has experienced mass extinctions from asteroid impacts, from massive volcanic episodes sustained over thousands of years, from violent climate transitions. Physics does not care about civilizations. All 8 billion people on one world means that one sufficiently bad event ends the entire story. Not just many deaths. The end of the story, with nothing left to continue it. A self-sustaining Mars changes that arithmetic. Not a resupply-dependent outpost that goes dark within months if Earth stops sending ships, but a world with its own industry, its own food supply, its own medicine, its own power generation. A world where, if Earth went dark tomorrow, 1 million people on Mars could keep breathing, keep farming, keep building, keep thinking indefinitely. That is a backup, not of data, of consciousness, culture, languages, genomes, and ideas. Once Mars reaches that threshold, humanity exits a category it has occupied for its entire existence, not a category of safety. The risk does not drop to zero, but it exits the range where a single asteroid impact ends everything. The species becomes harder to kill than any species has ever been. Planting a flag does not give that. A flag and a footprint give nothing that a photograph cannot. The redundancy comes from a complete technological stack that works in the harshest environment any human civilization has ever attempted. It requires reactors that run for years without maintenance from Earth, robots that operate through dust and cold without supervision, closed-loop ecosystems that do not crash, legal systems that handle scarcity and emergency without collapsing into chaos, cultures stable enough under pressure to hold communities together across decades. Possibly, eventually, humans biologically or cybernetically adapted to a world that never designed itself around their comfort. The harder you look at what a self-sustaining Mars actually requires, the more it looks like a problem that reorganizes everything it touches. And that reorganization does not stay on Mars. Let's stay with that idea for a moment. The reorganization does not stay on Mars, it comes back. The tech stack that makes Mars survivable is not custom hardware with no other use. It is a collection of solutions to problems that Earth already has, built under conditions that force them to actually work. High-efficiency water recycling designed to recover more than 90% of every litre, day after day, in a system that cannot afford to lose what it cannot replace. That same technology, applied to drought-zone cities on Earth, changes the math on water scarcity in ways that decades of incremental improvement have not. Autonomous robots designed to operate smelters, inspect reactor shielding, and repair exterior walls in cold, dust, and low pressure, without a human standing next to them. Those same robots building in flood zones, collapsed structures, contaminated industrial sites, places where sending a human is expensive, slow, and dangerous. Controlled environment agriculture designed for a sealed greenhouse on a world with 43% of Earth's sunlight and dust storms that can cut that in half, producing more calories per square meter than open field farming on Earth, while using a fraction of the water and land. Radiation shielding and monitoring systems engineered for a population that cannot absorb mistakes, changing how we manage nuclear power plants and how medical imaging equipment protects the people inside it. The tools built for Mars are not prizes stored in a display case after the mission. They are working solutions, and failing to apply them to Earth's problems while they exist would mean missing the point of building them. The reality is stranger than that. The technology is only the beginning of what comes back. Over generations, the people themselves begin to change. When every excursion outside means a pressure suit and an airlock, and Earth is not a flight away but a 6 to 9 month journey that costs more than most nations spend in a year, the word home stops meaning a planet. It means infrastructure. It means the corridor where your friends live, and the greenhouse where you tend the wheat, and the medical bay where you were treated after the pressure incident 2 years ago. A person born on Mars who has never seen a blue sky does not experience the absence of one as loss. It is simply the sky, red, thin, and vast. Their sky. But the drift goes deeper than aesthetics. Risk perception shifts. A colony making a calculated decision to accept higher chronic radiation exposure for its children, because the alternative is abandoning the project, and with it the species-level redundancy humanity is trying to build, is making a moral calculation that no existing legal or ethical framework fully addresses. Who decides what level of exposure is acceptable? The colony's elected council? A corporation that owns the reactor? Earth-based regulators receiving messages with a 20-minute delay? There is no clean answer. The colony will have to build one from scratch, under pressure, with lives depending on the outcome. New possibilities open alongside the new pressures. Gene editing targeted at radiation resistance, edits to bone metabolism, adjusted for a body that spends its entire life in 38% of Earth's gravity, building the skeleton it actually needs rather than the one Earth selected for. Neural implants for managing complex systems, for maintaining coordination across a colony where the AI is watching the sensors and the humans are watching each other, and the line between the two is not always clear. Cybernetic integration for coping with the specific kind of isolation Mars produces, not the temporary isolation of a submarine deployment with a known return date, but the permanent low-grade separation from a world that is always on the other side of a communication delay. The deep question is not whether these changes are possible. They are. The question is what they produce. A colony where humans are gene-edited and cybernetically augmented, raised in 38% gravity with different educational norms and a legal system invented locally, and a culture that has no living memory of Earth, governed by systems that range from direct democracy in small groups to strict technocratic authority during emergencies to company town structures where a single corporation owns most of the infrastructure. Are those people still the same humans as the ones on Earth? Culturally? Biologically? Or has humanity quietly split into branches of the same original species, each shaped by the world it actually lives in? Not a dramatic rupture, not a declaration, a quiet drift. Generation by generation, the category human becomes a broader container than it was. And Mars is not the end of that process. It is the beginning. Phobos and Deimos, Mars's two small moons, become the first logical extension. They are staging posts, fuel depots, low-gravity platforms where material arriving from Mars can be loaded onto vehicles without paying the energy cost of lifting it from the Martian surface. Local fuel production on Mars, already running to support surface operations, scales to supply those depots. Tugs running between them and the asteroid belt no longer need to carry all their propellant from Earth. The asteroid belt, once a remote map feature, becomes a reachable mining zone. Metals and volatile compounds in concentrations that Earth's crust, already stripped of its easiest deposits by centuries of extraction, cannot match. The closed-loop life support systems developed for Mars, combined with rotating habitat designs that generate artificial gravity, make free-flying habitats a real engineering project rather than a paper concept. Structures called O'Neill cylinders, enormous rotating stations where the rim spins fast enough to produce one full gravity at the edge, have existed as proposals for decades. They stay proposals until someone has actually built and operated the closed-loop systems that would make them livable. Mars provides that proof. The outer system moons, Europa with its buried ocean beneath a radiation-saturated ice shell, Titan with its thick nitrogen atmosphere and liquid methane lakes, become long-range targets, more extreme than Mars in every relevant dimension. But by the time serious missions are planned, the core capabilities exist. The closed loops work. The robots operate autonomously. The medicine handles novel environments. The governance structures, however imperfect, function under pressure. Interstellar precursor missions, probes sent ahead of any crewed journey to the nearest stars. Generation ships designed around the reality that no living person who boards will arrive, become feasible in a different way than they are today. Not because the physics changes, the distances remain what they are, but the engineering and the cultural infrastructure required to sustain a community disconnected from Earth for decades or centuries stops being purely theoretical once a self-sustaining Mars exists. Mars demonstrates that intelligent life from Earth can detach from its origin planet and continue. That is the test. Not whether the rockets are powerful enough, whether the civilization is robust enough. Pass that test, and the door opens, not just to the rest of the solar system, to a category of possibility that does not exist for a species living entirely on one world. Living on Mars is not a frontier myth. It is a long, grinding negotiation with physics and biology and engineering and human behavior, conducted under conditions that punish every mistake. The required deliverables are specific. Reactors that run for years without maintenance arriving from Earth. Robots that do not quit when the dust accumulates and the temperature swings 60 degrees in a single day. Closed-loop ecosystems that do not crash because a sensor drifted or a biofilm colonized the wrong pipe. Laws that handle sabotage and resource scarcity and medical quarantine refusal without collapsing into chaos. Cultures stable enough under pressure to hold communities together across decades when the nearest city is a 6-month journey away. And possibly eventually, new kinds of humans, biologically adapted, cybernetically extended, shaped by a world that never wanted them and made no accommodations for their arrival. The harder you look at what all of that actually requires, the clearer something becomes. This is not about changing planets, it is about changing us, not as a metaphor, as a literal description of the process. The first humans to stay on Mars will not be Earth people transplanted to a red rock. They will be something that learned over years and generations and accumulated failure and improbable success to turn a lethal desert into another branch of human history. The species that looks back at that process from wherever it stands in 1,000 years will recognize what Mars was. Not a destination, a threshold, the moment when life from Earth first learned that it could carry itself beyond the only world it had ever known, and survive the carrying and keep building. That is what is waiting on the other side of everything we have been talking about tonight.